What does this nice visual have to do with the positive definiteness of a matrix? Let's find out in this short tutorial. So first of all, how is it defined? Positive definiteness is only defined for symmetric matrices, and there are different tests. Are all of the eigenvalues positive? Or are all of the determinants positive? And here we go from the left upper corner determinant, the blue one, then to the red one over here, and then to the 3×3 determinant, for example. If all of these are positive, it means we have a positive definite matrix. Or we can also have a look at the pivots. Are all of the pivots positive? So all of these are tests that can prove the positive definiteness, but there's a nice visual intuition, and that is what I showed you in the graph below. We can just look at this expression here, x transpose ax. And if this is positive for all given x values, it means that the matrix is positive definite, and actually that's also the definition that is used. I created a function using Python SymPy that takes as a parameter a 2×2 symmetric matrix as an input, and it returns the quadratic polynomial. So let's see how this works. First of all, in SymPy, we need to define the symbols over here. So we have x1 and x2 for the 2×2 case. And then we define that the vector x consists of x1 and x2. And just compute x transpose ax with this over here. And to expand it, we use this function, just sp.expand. The quadratic form, and we get the expanded polynomial, which we return in this function. Okay, and then there's also a function to visualize this expanded polynomial. I will not get into the details over here. And so let's look at the sample case. We have this given matrix A1, 2, 6, 6, 20. Is this positive definite? So we run these functions, and it returns the expanded quadratic polynomial, which is 2x1 squared plus 12x1 x2 plus 20x2 squared. And this creates this graph over here. And that's the graph I showed you in the beginning. And you see that none of the parts of this graph extends into the negative space. Everything is in positive space, and it also doesn't hit this xy plane over here. So this is a positive definite matrix. Okay, and then let's have a look at this case, matrix 2, 6, 6, 7. And when we print this one, we get this graph over here. So now I zoomed out, let's zoom in. And you see that here we have red space, which extends into the negative section. And if any of the part of the graph is in the negative space, it means that the graph is not positive definite. So this is actually how we can visually tell about the positive definiteness of this matrix. And then we have another case. Let's look at this matrix, 2, 6, 6, 18. And here we see, when we plot it, that it doesn't extend into negative space, but we do see these dots or squares over here. And this just looks like an artifact, but it's not. It means that the graph actually hits the xy plane over here. These are zeros, basically. So when there are zeros, it means that this graph cannot be considered positive definite, but it would be positive semi-definite. So these are just some visual intuitions to understand the positive definiteness of a matrix. Of course, this only works in 2×2 case in 3D space, and the other tests will work better if you have to get the proofs, but this is a nice visual intuition for it. And SymPy itself also has a function, of course, that can directly tell you if a matrix is positive definite or not. It's matrix.isPositiveDefinite. And you see below, for the 3 that we checked, we get for the first one true, and for the other ones false. Also the positive semi-definite case is false. That's all that I wanted to show you for today. Thanks for watching, and hope to see you soon again on this channel. Don't forget to like and subscribe.